Hello everyone. Today we'll talk about a solution to the problem minimized maximum of products distributed to any store. This is a kind of problem that I tend to visualize as a sort of staircase problem, in that we have a staircase that has some steps, maybe some steps are of the same height, and we have that staircase of course be non-increasing because we want to have it as a staircase. And our role is to make this top floor as low as possible. So the biggest step on our staircase to be as small as possible. And this is indeed the case in our task, which just comes from the fact that we want to minimize the maximum value of some array. And for instance, if at that point we were able to, let's say, half the height of any step, so let's say cut this step in half, then this step would transfer here, and now those two will be the next top step. We have some number of moves and we want to minimize the top step. And there are some approaches that work for most problems of that type. One approach, which will be the approach that I'm going to show you in code, is that a staircase like this can be efficiently simulated by a priority queue. While a priority queue really does not think of the rest of the staircase in a sorted fashion, that would require a binary search tree. But a heap will always remember the biggest step, and the biggest step is the step that determines the maximum that we want to minimize. So this will be the solution I'm going to show, the solution that will just maintain this priority queue. But the key idea anyways is that you might think of, if of course all the moves are either indistinguishable or they depend only on the current value, the current height of a step, that you can always operate on the biggest step. Because operating on something else will not decrease the biggest step, so you might as well just decrease the biggest step immediately instead of doing it later. And if you weren't going to do it later, then any move that does not decrease that step is not optimal. So you can either simulate it, and that's what we're going to do here. Sometimes you can tell immediately by looking at a step what you need to do to ensure that this step is low enough. And sometimes you don't know that, but you can use a trick to know that, which would be binary search on the answer. Because we don't know in our problem how small the given step should be. So in our case, it's how many stores should get their fair share of some product type. But we can use binary search because if it's possible for the staircase to be lower than some value, then it's also possible for it to be lower than all the greater values. So we can ask, is it possible for our staircase to be lower than 10? So for every shop to receive less than 10 items of the product. And in that case, if we have some product for which we have 15 copies, we know that we have to distribute it among 2 stores at least. And if we distribute it among 2 or more, then it's okay, less than 10. Otherwise, it will not be okay. So we know exactly how many stores need to get a given product. And that binary search will just try to guess that value, try 10, then try 5, then try 7, then try 8, and maybe end up with 8 as the result. And at every step we have to go through all the steps, calculate how many moves we have to make, so how many shops have to get that product. And if the number of shops is less than or equal to the number of shops we have available, then we're happy, it's possible. Otherwise, we're unhappy and it's impossible. And we adjust the direction of search in the binary search accordingly. So the solution that uses priority queue, so we'll always maintain the biggest step, is very simple to implement because we have to have a priority queue. It has to be sorted based on the ratio of the number of products to the number of shops that have that product. So at the beginning, one shop has that product, and we have, of course, queue of that product for queue in quantities. And we want the sorting to be done on the ratio rounded up, and we want, of course, to get the highest value. So the ratio at first is q, and we'll be maintaining negative values because if we maintain negative values, then we get maximum heap, in essence, if we remember to negate it, because the heap will always give us the smallest value, and the smallest negative value will be the value which has the biggest absolute value, which is what we want. Now, the number of steps, the number of times we can split a product into one more shop, is the number of shops minus the number of products, because every product has to go to at least one shop. So after we've heapified our list, so created a heap. At every step we take the one with the biggest ratio, so we have the ratio, total, and count. We don't really care about that old ratio. We care about the new ratio, which is total, divided by count. The new count is bigger by 1. We have to round it up, so to have divided by count rounded up, we get total plus count minus 1 divided by count rounded down. This is the same as divided by count rounded up. And we push it back on our heap. So we push the negative of the new ratio, total, and this new count. And at the end we look at the product that has the biggest count, the biggest ratio. So this is again just the pop. We take its ratio, we negate it, and this is our result.